I muted myself. Hello, good evening. Can you guys hear me? If you can type yes or no. Okay, great. Thank you, Jonathan and home friends. How about, can you see my screen? Okay, wonderful. All right, good evening, everyone. I want to say happy Christmas. No, it's happy Thanksgiving. All right, so this is holiday. I appreciate everyone to be here because I know in holidays you do what you really like to do, right? So I appreciate that you guys are here and take the take this lesson. Okay, so all right. So before we start, I will go over a couple of things. Quickly go over a couple of things. The first thing is, someone asked me what if I miss some lessons, previous lesson, right? So I'll tell you this class, the order of the lessons, it doesn't matter. Okay, so you can pick each time we're going to cover a topic. These topics not necessarily related. So if you miss one, you still can take this one without the previous one. So this is one thing I want to say. The second thing is, I think most of us were able to submit our assignments. But if you haven't complete all of them, this is a good time to catch up in the holiday, Thanksgiving days, right? Trying to catch up as much as you can. It is very important that we submit all the assignments. Okay, doing homework is the most important thing for this class. Okay, if I don't see 2 submissions of yours, our TA probably gonna notify your parents. Or otherwise, you can tell me. Maybe you say, "Hey, Dr. Meng, I got some exceptions because what, right? So please allow me a couple of more days," which is fine. Just shoot me an email. I not necessarily have to tell your parents. I mean, my purpose is I want you to learn. I want you to submit your homework. All right. So, if you know that, I think you should have. What is my email? Okay, so let me type my email. Yeah, you can send the email directly to my personal account. Okay, for anything that you want to talk to me. All right, so but don't use that. Don't ask questions. Okay, don't ask questions in my send your questions to my personal account. Why is that? Let me tell you why. Okay, so this is good for you. Whenever in your whole life, it is very important that you create your your own community. Okay, you're gonna live in your community. Rather you live in a paid environment. What does that mean? Okay, you pay your tuition, so you hire a teacher. So teacher is responsible to answer your questions. But this is the rare case. Okay, what I want to what you want to learn is how can you communicate with people around you to get the resource to help you, right? So this is more important. Okay, so if you can send it, if you can ask in the office hour session, if you can send your question to the Discord group, and people can help you. Okay, well, one thing to remember, that is not the place people help. Only for people to help you. That is the place for you to help people as well. So a community is something like we can help each other, right? That's why we want to build a community. All right. So, essentially, I want to say, you should have sufficient material. You have the walkthrough for homework. In the first office hour session, our TA gonna, most of the time, our TA gonna give you a walkthrough. We'll lead a group discussion on a homework assignment, right? And also, after the due day, you should have a solution. The solution is there. But let me tell you one thing, you probably know that, right? For programming, there is no absolute solution. Okay, so people can solve the same problem with different ways. One could be better than the other. But anyway, try to solve by yourself. And then you can refer, you can watch, you can use the solution as a reference. All right, so today we're going to invite Kevin Main to take this lesson for us. Okay, Kevin is a student from MIT. He's majoring in EECS, which is electrical engineering and computer science. Okay, if you know MIT, they have like a CS plus whole lot of things. EECS, that's electrical engineering plus computer science. That is it. The code is 6662. Okay, what is a 6.3? 6.3 is CS by itself, and 6.4 is CS plus artificial intelligence. I don't remember all the code, but I know 6.7 is computer science plus biology. 6.9 is CS plus psychology, and the 6.14 is CS plus urban planning. I even don't know what, I'm not familiar with that subject, but it's something, it's engineering, or maybe it's a, it's a urban planning, right? That's about it. So yeah, Kevin will reserve some time for us to ask any questions. Yeah, it can be any questions. So whatever you want to, how to learn this, or what was your experience. Even you can ask, well, music is good for when I study. Is a music is good or bad, right? It's disturbing, or it is a it is a good thing for, is a good companion for us to study, right? So you can ask any questions. All right. So that's pretty much all I want to say, and then I can hand over the time to Kevin. All right.
Yeah, sure. Thanks. Awesome. So one thing before we get started, I think it'd be awesome if people who can turn on their cameras, turn them on. It really helps me get a sense for how well people are understanding things. I know that Zoom is a little bit different from in person, but I'd like to make it as interactive as possible. So please, it'd make me really happy to see all of your faces. Thanks for joining me on this holiday weekend. Awesome. Good to see all of you. Okay, so I'm going to go ahead and share my screen, and then we'll get started. Basically, how it's going to work today is I will talk a little bit about a problem. I'll talk a little bit about a problem that demonstrates an important problem-solving paradigm that's called greedy algorithm, like the greedy algorithm. By the way, can people see my screen?
Yes, I can see.
Yeah, I think to monitor questions, I'll have to join on a separate device because when I share my screen, it hides everything else. So give me one moment.
Yeah, Kevin, I can see your screen.
Yeah, I know. I can't see the chat, which is a problem. So 1 second, bear with me. I'll be in very soon. But yeah, I hope your Thanksgivings all went well and you ate lots of good food and you're ready to go back to school. I don't know how long Thanksgiving break is for you guys, but I hope it's enough. Okay. 1 second, disconnect audio. Okay, can someone type something in the chat so that I can just make sure that it's working? Nice. Okay, cool. Thanks. Okay, awesome. So Uh, Today we're going to be talking about greedy algorithms. Just so I can get a sense for the room, how many of us have heard of have heard of greedy algorithms or like this concept? Feel free to like raise your hand in the chat or use an emoji reaction or something. Okay, cool. So not a lot of people. That's awesome. Okay, so hopefully this will be a useful thing. Nice. So when you first hear the term greedy, what comes to mind? Like, does it hint at any like possible way that we could think about solving problems? Is it very suggestive of like a certain way that we should approach things? Um, like what does being greedy mean to you? Okay, awesome. I see a suggestion that says take options. Exactly. So a lot of problem solving and a lot of, in fact, it turns out a lot of problems in computer science can be reduced to the idea of making decisions. And um and I see a lot of great suggestions in the chat. We have like getting the most out of something, taking the best options. That's all very fine and good. The key about greedy algorithms is that you're not only going to take the best option, you're actually going to take the best option in the moment. For example, you might imagine when you make decisions, you could imagine like if you make decision A, you could rule out other decisions that could have made you happier. Like let's say you're trying to optimize for your happiness and you like make the decision to book a trip to, let's say, France. Um, Even though like if you looked around and let's say or let's say that you're trying to plan a trip and you're trying to choose the cheapest trip possible, you can think about booking tickets. And when you book tickets, you can just go on, go on Google and type in tickets to anywhere in the world, and then you can choose the cheapest ticket to anywhere in the world. And that's the locally greedy option. But like the problem is you haven't considered once you actually get to your destination, how much money are you going to spend? Like um say that you decide, okay, well, it's super cheap to go. If I'm currently in Boston, it might be super cheap to go to New York City or something like that. And so you book your flight to New York, but then you realize that New York is extremely expensive. And then you end up making a lot of decisions in New York to like spend money, and you end up spending more than you would have if you decided to book maybe a slightly more expensive flight that would take you to Cleveland, Ohio. But Cleveland, Ohio is a lot cheaper than New York City. And so if you add up all the costs, it would actually have been cheaper if you went to Cleveland. So where did we go wrong when we were making this decision, when we were looking for the cheapest trip possible? Does anyone want to suggest an idea? Like, why did we go wrong? Why did we end up choosing the more expensive option? Yeah, exactly. So we only considered a very local part of our decision. We didn't consider all the other things that would happen once we actually made that decision. So these are all excellent points. Like you failed to look ahead. You made this local greedy choice that was good and fine. But then when you look forward and then you analyze the consequences of your decisions, you realize you actually messed up. And so that's actually the key thing that we'll have to be careful of with greedy algorithms. So the idea behind a greedy algorithm is that it's super simple. And the classic example of this is giving change. So imagine like you go to the movie theater and you buy some popcorn that costs $4.63, and you hand them a $5 bill. Does anyone want to propose an algorithm for giving change so that you hand over the minimum number of coins? It's sort of like the intuitive thing. The whole idea behind greedy algorithms is that it's super easy to come up with a solution, but it's very hard to prove that your solution is actually optimal. And so, yeah, I see the correct answer in the chat. So you basically choose the largest coin value you can give without overshooting, and you choose that coin. So for 463, how much change do we have to give back? Does anyone want to do quick maths in their head? For 463, and we give, if I give you $5, how much change do you owe me? Yeah, exactly. So you owe me 37 cents. And what's the biggest coin that you could give me without overshooting? It's a quarter, right? Like 25 cents. So then you give me your quarter, and then you realize, oh, I still have 12 cents left. And then you give me a dime, and then you give me 2 pennies. And that's the solution. That minimizes things. Now, is it obvious to you that this is actually the optimal solution? Is it obvious to you that when I gave you the 25 cents, it wasn't, because I wasn't looking ahead, I might have failed to spot another opportunity to give you fewer coins? So it could be obvious to you, but it's also not super, super obvious if you think about it carefully and if you want to come up with a very rigorous argument. So that's the whole idea behind greedy algorithms. Hopefully this gives you a sense for it. It's sort of like you don't have to look ahead. You can just make the optimal choice at every single step, and then it'll happen to turn out that if you keep following this greedy policy, you will find the globally optimal solution. And so in the case where we were trying to plan the cheapest vacation, we failed, right? The greedy algorithm failed. And in the case where we were giving change, the greedy algorithm succeeded. And so greedy algorithms are a little bit tricky because they're super intuitive, but you can often apply them incorrectly, and they'll often give you the wrong answer. So the key is doing lots of practice and thinking a lot about greedy algorithms so that you can actually carefully show that they'll actually work properly. And usually it just comes down to a lot of practice and a lot of intuition, but I'll also provide a few guidelines for ways to think about greedy algorithms and greedy problems so that when you see a greedy problem, you'll sort of just be able to spot it. Cool. Does that make sense? Does anyone have any questions so far? Feel free to send them in the chat if you have any questions here. Okay, awesome. Yeah, so I think we can probably move on to the problem and let's see how it treats us. All right, so here's the problem. I've pulled it up on my screen. And it's about some Farmer John's cousin Ben, who's a mad scientist. So let's read through this together. So this first paragraph is just bloat. It doesn't really matter. So Farmer John has cows. He currently has N cows. Notice that you have less than 1,000 of them, which is important. And so you have 2 different breeds. You have the H breed and the G breed. And so to determine like what actually you have, so for each cow, we'll identify them by either the character H or the character G, H for Holstein or G for Guernsey. And they'll be presented to us in the sample input just as a string. So you can see in the input format, it says we have N of them. That's the N right here. And then the next 2 lines contain the strings A and B. So each string is N characters that are either H or G. So apparently there's like 2 strings that we have to take care of, but essentially the idea is every string represents a set of cows, and every single location will tell you that cow, which breed is it. So like the first cow is a Guernsey, the second one is a Holstein, and etc. Cool. So now we have to figure out what these 2 different lines mean and what they correspond to. Okay, so let us call these 2 strings A and B, where A is the string of the breed identifiers Farmer John originally wanted, and B is the string that he sees when his cows arrive. So basically, he has ordered some cows probably, and he expected certain cows, and then he got certain cows. So the company that was delivering cows probably messed up. Farmer John requested these cows, and unfortunately, they returned these cows. So they messed up. And so what are they going to do about it now? After several months of work, Ben creates a machine. It's this cow breed flippinator that can take any substring of cows and toggle their breeds. So does anyone want to remind me what a substring is, or like what does that mean? And if you don't know, feel free to just type in the chat. I don't know, because we can talk about that. It's just a little piece of terminology. Yeah. Okay. Cool. So there's actually 2 concepts that are important here. The first one is, well, there are 2 things that we have to draw a distinction between. The first one is a substring, and the second one is a subsequence. Does anyone know what the difference between these things is? Okay, cool. No worries. It's just a little piece of terminology that we'll have to cover. All right, so why is my pen lagging? Uh-oh. Okay, whatever. So a substring, like people said, is just a string inside string. It's just a string inside of a string. So a string itself, so first maybe we should define string. A string is just a sequence of characters. You can imagine just like a piece of text. That's what we call a string. In MIT App Inventor, it's just a little text block that contains a string. A substring is just any contiguous sequence of letters. Contiguous sequence of letters. And contiguous means that you can't have any breaks in the string. For example, in this input, HHH is a substring, HHG is a substring, GHH is a substring, but is GHH, like, are these three, do they make a substring? Feel free to answer in the chat. No, exactly. Does anyone want to take a guess at what this would be? This weird GHH sequence, because there's a specific name for it. It's the other thing that I brought up. In fact, what this is called is this is subsequence. Exactly. So a subsequence is basically just a sequence within the string. By the way, all of these have to be in order. You can't just like go out of order and choose a substring. They're all in order, but the substring has to be contiguous while the subsequence does not have to be contiguous. So you can skip around with subsequences. And when you start looking into this thing called dynamic programming, which maybe will not be covered in this course, but will probably be covered once you advance further into computer science. Dynamic programming will be will have relevance to this idea of a subsequence. But for now, we'll just deal with substrings. So there's a question: what if I do something like A B C D E or A B C D E? William, could you please clarify what you mean by this? It looks like the only difference is that there are commas in between, right? So what do you mean by that? But yeah, if anyone has any other questions about what it means for something to be a substring, feel free to let me know. So for William's question, remember that a substring has to be within another string. So if you had a string A, B, C, D, E, A, B, C, D, E is a substring. A, B, C is a substring, B, C, D is a substring, D, E is a substring. All of these are substrings. But for example, E, F, G, H is not a substring because it's not contained within this original string. Does that make sense? Okay, cool. All right. So back to the problem, it says it can flip any substring of cows. So you line these cows up in order, and you can choose any contiguous substring of them to flip. Remember, you can't skip, which is what makes this problem a little bit trickier. So when you flip them, all H's become G's and all G's become H's. And Farmer John wants to figure out the minimum number of times he needs to apply this machine to transform his current ordering B into his original desired ordering A. So basically what this problem is saying is Farmer John, he wanted this string. This was Farmer John's desired cows. No, iPad lagging. Okay, so FJ's desired cows. And then there was what he received. Basically, you want to turn this string into this string with a minimum number of applications of his flippinator. Now, the first thing you might think is, well, why is this even an interesting problem? Well, if we take a look at this example here, how many indices differ? Does anyone want to point out which cows are incorrect here? And then maybe that'll help us find, that'll inform the way that we think about this problem. Which cows are messed up here? You can use 0 or 1 indexing, it doesn't really matter. But just like, which ones are incorrect? Which ones do we have to fix? Yes, exactly. We need to fix 1. This is 1. We need to fix 3, and we need to fix 4. So just intuitively, how would you apply the cow flippinator to use it the minimum number of times? Remember, if in one fell swoop, you apply it to all of these cows, like indices 3 through 4, 5, 6, 7, 3 through 7, if you apply it to all of these cows, that only counts as one application of the machine. So that's where you can make things optimized. So how many applications of the machine do you think we need here, and why? I know that the sample output is right here, but also try to explain why. Yeah, exactly. So we need 2. We need 1 for HHGG, and we need another for GNH. Exactly, that's right. So does anyone have any ideas for how we might solve this problem? Any initial just ideas based on this idea of greedy? Like, greedy solutions often are the first things that come to mind, and they're really brain dead solutions. They're like super simple, and they make choices that seem to be too good to be true, but then you just write your solution out, and then we think about it and figure out whether it's optimal or not. Okay, so Evan suggests to find the differences, right? So yeah, maybe the dumbest thing that Farmer John could do is to apply this machine at every single index that differs. But how could we optimize that? Because here, there are 3 indices that differ, but the actual answer is actually 2, because we could apply these 2 together and deal with them together. So I do agree, maybe the first goal is to find all of these differences. But what should we do after that? How do we take this difference data and turn it into a solution? Okay, so there's a suggestion. Find the number of chunks in the differences. In this sample, there are 2 of them. And so that will give you the solution, right? So that is a greedy solution because, I mean, if you think about it, there is like a weird, tricky way that you could solve problems like these. If you ever had, if you ever had a sequence that was like H, H, G, 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 and you had some that were wrong and some that were right. Let's say that these were wrong, but these were right. And then you had another one that was wrong here. I guess another way that you could do this problem is, and so if we applied the current technique, what would we do? We would find which ones are incorrect here. Which ones would be the differences? If we had this sequence. Exactly. So we have 1, 2, and 5 that are incorrect. Some of you might think, well, isn't it sometimes more efficient to come in and do this kind of flipping? We can flip the entire thing. We can apply the reversinator over the entire sequence. And so we would get what? We would get H. We'd get H. Oh, maybe I should write it in a different row. So if we apply the flippinator over the entire range, we would get H, 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 G. And so now which ones are incorrect? Which indices are incorrect? Yeah, exactly. So now we have that 3 and 4 are incorrect. And then now we would just apply the flippinator here. And then we would get G and G. And then H, H, G is still there. And then we would have these 2 match exactly. So why shouldn't we do this? Does anyone have any observations that they'd like to make about this kind of approach? Right. So the first thing is that it's less intuitive. It's a little bit trickier. It's not exactly greedy, because then you have to make the decision, well, when do I actually flip cows that used to be correct? In the other solution, you can think of it as greedy because we only looked at the cases where the cows were incorrect, and then we just tried to minimize the number of flips that we needed to make those correct. But here we're doing this like weird, tricky stuff where we're actually flipping cows that used to be correct. Now they're actually incorrect, and we don't want that. But somehow it seems to be possibly efficient. So does anyone want to make any other observations about this technique? Anything about its efficiency? Anything that you notice that's a little bit weird about this strategy? Anything at all that might inform whether we should take this strategy that's a little bit trickier, but possibly more efficient, we don't know, or this strategy where we just directly look at all of the incorrect indices and then flip all of them. Ah, yes. So Evan is right. He says that the flipping of the entire sequence was pointless. So the first way to notice this is obviously, if you did it the greedy way, you would just flip this section and you would flip this section and you would take 2 moves. And here, when we did this weird global thing, we made this move and then we made this move. So we ended up making 2 moves again. So in this case, it didn't help us. Do you think it'll ever help to do this weird like global thing where we flip everything and then we flip it back? Is it always true that this is the same or less efficient? Oh, okay. So William says no, but Evan says yes. Does anyone want to? Okay, now Evan says no. Interesting. Yeah. See, this is where greedy algorithms get a little bit tricky. You have to think carefully about whether greedy algorithms actually work. You know, it could have been a trick. Like I could just be messing with you. Like this entire problem, even though the topic of the lecture is greedy algorithms, this isn't actually a greedy algorithm. That could be the case. So you need to think carefully about whether it's actually greedy. And while you guys think about that, I'll answer Ray's question. Can you explain the last move again? And Ray, are you talking about this whole sequence where we did this stuff? Just type in the chat yes if this is what you want to be re-explained. Okay, sure. So let me get rid of all this. Let me move this all away. So just for those who might not have gotten it the first time I explained it because I moved a little bit quickly, say that you had this sequence. And so Ray, you agree that these are the ones that are incorrect, right? Okay. So our greedy solution would say, okay, well, these are incorrect. So we'll just flip these 2 together and we'll flip this one and our answer is 2, right? But instead, what we might actually want to do, possibly, is flip the entire row first. So let's flip the entire row first. What will we get? These 2 become H. In fact, all of these become H. And this one becomes G, right? Now which ones are wrong? So these 2 got fixed. Now these 2 are incorrect. And this one got fixed, right? So now we can just flip those 2 and get a 3rd round. We have a GG. And in fact, because we didn't flip these remain the same. And so now you have that these are right and these are right, right? So these are the same. And we took 2 moves. So we took 2 moves, right? Does that make sense, Ray? Does that answer your question? Cool. Nice. All right. Great. So here's the trick now. Is this actually ever necessary? Is this ever necessary? So for people who gave their opinions, so William and I guess Evan, why do you think that sometimes this non-greedy thing is necessary? And I think somebody else, Yifan, if you would like to, you can go ahead and explain why you think this always works. Or the greedy solution is always work. It always works and we'll never have to use this weird, strange global thing. It's kind of a debate because this is the crux of the problem. If you can figure out whether this is legit or not, and if indeed if you find out that it's legit, the implementation is dead simple, right? But the hard part is figuring out whether it's valid. Okay, Evan, so you think that it sometimes works. Can you point out an example where it does not work? And for Nancy, the greedy solution is just to look at the string and be like, oh, in this string, G and H are different, H and G are different, H and G are different. We go to these strings and we just directly flip as much as we can. So for this one, we can only flip it by itself because it's alone, but these two reside in a chunk, so we can flip them together. And so we do 2 flips, and this is 2 in total. Does that make sense, Nancy, for the greedy solution? Okay, cool. Yeah, so that's the greedy solution. Basically, we're saying you don't care at all about the things that are already correct. We'll never want to flip anything that's already correct. Instead, we'll just look at everything that's incorrect, and then we'll flip as much as we can at the same time, and making sure never to touch the things that were already correct, right? Okay, so Evan has proposed a greedy solution that he thinks does not work. So let's look at it. Or an edge case that fails the greedy solution. All right, so Evan's proposal is to use H, H, H. Let me write this out a little bit more spaced out. The proposal is to use H, 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 G, H, and H, 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 H. Okay, so Evan, what do you think the greedy solution would do? Oh, you're saying that this one works. Okay, which one does the greedy solution fail on then? Because you said that it sometimes works. Right. So can you think of any cases of greedy failing? Or do you think greedy always works? So let's take a vote. So for everyone in the class, it doesn't matter if you're right or wrong, because the whole process is learning through proving that your old opinions were wrong. So type a yes in the chat if you think that the greedy solution is right and that it's always optimal. Or type in no if you think that the greedy solution fails in some cases and we haven't thought carefully enough about it. Okay, so there are quite a number of no's and also quite a number of yeses. It's almost like 50-50. This is fascinating. There seem to be a few more yeses than no's, but the tricky part is being able to explain yourself. Okay, yeah, so for Ray, the question was, if you think the greedy solution is always good, like you can never do better than the greedy solution, type in yes. And if you think that the greedy solution can fail, in other words, it'll give us the wrong answer, type in no. Okay, great. So Evan has another failure case. No, so the greedy one is the one where we only look at it's the one with no weird flips. We only look at the ones that are already incorrect. Like for example, these 3 indices, and we flip as much as we can within the wrong indices, but we make sure never to touch the correct indices. That one's greedy. So if you think this is always valid, then you type yes. And if you think that there are problems with this, for example, in cases where we would need to flip the entire thing first and then do a mini flip at the end, then type in no. Okay, cool. So Evan has a failure case. Great. Let's look at it. This is awesome. So Evan's failure case is this. Let's write it out. Okay, so it was G, 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 H, G, G, H, 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 G, H, H, G. So greedy doesn't work here. Great. So let's look at what the greedy thing would do. So first, let's point out which ones are incorrect. This one is wrong. These are all wrong. These are all wrong. These are all wrong. These are wrong. Did I write this down correctly? So all of them are wrong, right? Yeah, okay. So all of them are wrong. So what would this greedy solution be? You flip these 3 together. you flip these together, you flip this one, you flip this one, right? You get 1, 2, 3, 4. You get 4. Oh, wait, sorry. I'm confused now. You could flip all of them at the same time, right? Okay. So for Evan's failure case here, the greedy solution would just flip all of them at the same time for this case. So that's definitely optimal. Do you agree? Okay, so Evan has changed it. So he has another failure case. G G G H G G H H G H G H H G. So there's one that's correct, right? So we have all of these that are incorrect. So our greedy solution would do 1, 2, 3, 3 flips, right? Do you agree? Oh, sorry. Yeah, I'm trolling. Okay, yeah, it would do 2 flips because this one is the same. And then how does greedy fail here? What would be the optimal if we didn't have to do 2 flips? Right. So the other solution would just be to flip all of them at the same time and then flip the second one, which also gives you 2 flips. So is this a failure case? Okay, Nancy also has a failure case. So I think we can all unanimously declare that this is not a failure case. It seems like greedy happens to work here, maybe by accident, who knows? And often, you got to be careful because edge cases are very tricky. And like it can work for 99% of cases, but then you can get surprised by something weird. So let's try Nancy's case. We want to be complete. And then once we try more and we get some more intuition, we'll take another vote and then we'll see how we can actually prove whether this is actually good or it's a bad algorithm. Okay, so Nancy has a failure case. It is G, H, G, H, G, H, H, and you want it to turn into all H's. Okay. Let me see. So this one is wrong, this one is wrong, and this one is wrong, right? So our greedy algorithm would output 3 because you just flip them all independently. So here's the interesting part. What happens when you do the whole flip? So for Nancy, what would be the better solution? And for William, FYI, the HHH thing, you can just flip all of them at the same time. And so 1 would be the output for greedy and would still be optimal. Okay, so for Nancy's proposal, let's take a look. Let's try another weird algorithm. Let's try flipping these 2 first and then these 2 first. This seems to be suboptimal, but we can try it. You flip these 2, then this one gets fixed, then you have to flip this one again. But then you have to flip this one again and these 2 again. This is actually pretty terrible because you have to flip 5 times. You can actually do better. And so for William, yes, we're talking about if greedy fails. So we're trying to come up with all these cases to see this darn greedy algorithm fail so that we can finally show once and for all that it's a bad algorithm. That's our goal here. Okay, so flip the first 5, then flip 2 back. Okay, so flip the first 5, right? So this is 1. Then we flip this one and we flip that one. So this is 3. Seems to match the greedy algorithm, right? Do we all agree? Yeah, it is, it works. Okay, so now that you've seen some empirical evidence, has anyone updated their beliefs? Now let's do it. Let's revote. How many people, if you think that this greedy algorithm is good, type yes in the chat. Otherwise, type no. Okay, so a lot of people are starting to cave. Any brave soul want to offer a no and explain why? Okay, it looks like everyone's agreeing. Ah, okay. So somebody has voted no. People are still deeply suspicious of this algorithm because it seems really too good to be true, right? It seems like you could do something smarter. You could knock out more stones with, you could knock out more birds with one stone at the same time when you flip a bunch of stuff at the same time. So there are still some naysayers. And for the people who say no, is there like does anyone, and you're totally right, Nancy. I love this mentality. You should totally be afraid of edge cases. They are what get you. But it turns out that we can show through an argument that it is one way or the other. So for anyone, like even if you said yes, even if you said no, is anyone able to offer like an argument? It doesn't have to be very formal, but it's just sort of like an intuition for why they think their answer. Okay, so Nicholas has a proposal. By flipping some of them and then flipping the middles, you split them into amount of splits plus one intervals, meaning you could either flip those split plus one amounts or flip some amount, then do the splits, making the amount of flips the same as the greedy algorithm. Aha, this is awesome. Okay, so Nicholas has basically just given us a proof sketch for a proposal. And his proposal or his claim is that the greedy algorithm is actually optimal. So Kevin also has something here. Break it into two cases, both sames at the end, both differences at the end, same at one end, difference at the other end. Right. Okay. So the tricky thing about Kevin's proposal is that you kind of have defined the problem recursively, because at every step you have two cases, but then you got to figure out like what's going on in the middle. So you have to make that bridge between this case and then the little case that's inside. Okay, we have another proposal. I think the greedy algorithm will still work, since every correct answer that is taken down with the incorrect ones must be flipped back, thereby causing the greedy algorithm to take the same number or even less flips than other ones. Yeah. Okay, so some good arguments coming in. These are all in favor of yes. Does anyone that says no want to offer a more formal argument like the brave souls on the yes side have so far offered? I'll give you guys a moment to think about it. And then if you decide to change your mind, you can type in never mind and we can I think so. There are an infinite number of combinations. Sorry, infinite number of combinations of like orderings or yes. So you are correct that we have to think about all of these situations. And even if one of them doesn't work, then it is not optimal. That's right. For Ray, to give the others a little bit more time to think, after I explain this thing to Ray, I will finally reveal the correct answer. Or no, I won't reveal it. We'll think about it together and we'll come to the right answer to determine whether this darn algorithm is good or not. For Ray, the last technique is basically, the intuition is that if you ever have, we can use one of these examples. Which one of these is good? This one is good. So for Ray, the intuition is if we have these two strings, and we have these that are incorrect, we want to flip these. The intuition is kind of like, well, it seems like we could get a lot of work done by flipping everything at the same time, right? Because like we have these three that we have to flip. Why don't we use like a long thing to capture it and flip all of them and then deal with the things that we messed up later, right? That's sort of the idea. So if we flip all of these, then we get what? We get G, 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 H, H. Now which ones are incorrect? Ray, you tell me. Sorry, oh, sorry, I meant like comparing this one to this one, which ones are incorrect? Oh, you're giving it to me in zero index. Yeah, or like, yeah, okay. Yeah, 135 or 246 are both valid answers. Okay, so now we have that these two are wrong. Sorry, not like 135. I meant 24 or 13. So now that we have these are incorrect, maybe we just flip both of them. You know, we can either like flip each one individually, then the answer would be 3. Or you could imagine we could flip all of these at the same time. And then now we get G, H, 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 G, G. And then we would flip finally this one because this one is incorrect. And then we'd flip this one, and then we would also get an answer of 3. Does that make sense? Basically, you do as much work as possible, and then you kind of fix your mistakes later. Yeah, okay. All right. Cool. So I've been drawing this out for a while just to show you how difficult it is. Possibly that it could be for you to come up with a proof or a justification for why you think your greedy algorithm works. And so let's think about it. Let's think about it. I'm going to give some kudos to Nicholas because his explanation is actually spot on. You can think of this in terms of like subcases, and we can use this one as an example. So I'll copy this over. So let's look at Nicholas's solution and see. Let's see what he says, and let's check it out. So by flipping some of them and then flipping the middles, you split them into several intervals. So basically, Nicholas's observation is that, so these are the incorrect ones. Even if you decide to flip these, you're going to have some problems, right? You're going to cause some trouble in the middle. And the whole point is that these you never really want to flip because you're just going to end up doing extra work to bring them back, right? If certain cows are already in the correct form, it almost never helps. It actually, in fact, never helps to flip them because you'll end up having to flip them back anyways. That's kind of the main intuition. So let's formalize this a little bit. If you have a certain number of, oh, my headphones are dying. Oh, it's fine. If you have a certain number of intervals here, so currently we have 3 intervals of broken cows, and we could actually flip this one to make the example a little bit more instructive. So we have 3 intervals of broken cows. So our greedy solution would just be 3. What would be the case if we decided to use the non-greedy solution? Well, we have these 3 intervals that are incorrect, but we flip all of them. Let's like flip all of them first. That already takes one of them. But what have you actually done? So your greedy solution would have given you 3 intervals. You actually, because you have 3 intervals, you know that they're separated by at least how many, if there are 3 intervals, how many sections of good cows are you flipping to be bad now? And yes, Kevin, that's a very good abstraction to think about the problem in terms of. So what Kevin says is that you can actually just ignore the number of cows that are, number of cows that are in each of these chunks. You can just say you have this chunk that's bad, this one is good, this one is bad, this one is good, this one is bad, and this one is good. And this one corresponds to these 2 cows for clarity, right? So this is an easy way that we could abstract the problem. But here it's not super complicated, so we might not necessarily need it. Okay, but going back to our original thing, if our greedy algorithm says that there are 3 chunks of cows for which they are incorrect, we know for sure how many good cows are in between. how many chunks of good cows are in between if we have 3 chunks of bad cows? Anyone want to offer up an answer? So maybe I wasn't clear enough about my question. So that's probably my bad. I didn't ask a good question. Okay, yes. In fact, my question was a little bit vague. So first of all, do we all agree that it would never be necessary to flip cows outside the range of the bad cows? Like we would never go out here and flip all of these, right? Does that make sense to people? Yes, in the chat if it makes sense. Like we would never want to flip this one for no reason. Yeah, so we would never want to flip these for no reason. So we can always assume that the interval that we flip always ends with bad cows, right? And so in this interval, our greedy algorithm says that we have 3 chunks of bad cows. What does that directly imply about the number of chunks of good cows that are in between? In fact, like the hint is that you know exactly how many chunks of bad cows are in between. Yeah, exactly. Felix is right. It's just bad cow chunks minus 1. Why? Well, just think about it, right? If you had at the edges, you know that there are bad cows on the edges. If there was only 1 chunk of good cows in the middle, how many total bad cow chunks would you have? Exactly. You would have 2 of them. And if you had 2 good cow chunks in the middle, then you would have 3, just like we see in this case, right? So we can actually write out an expression for the number of good cow chunks in the middle. So if you have number of bad cow chunks, then the number of good chunks, I'll just abbreviate them CHKs, is equal to number of bad chunks minus 1, right? Does that make sense to people? This formula here. If it doesn't make sense, please type in like a question mark in the chat. Okay, excellent. It doesn't make sense. Does anyone else have any confusion about what this means? Does anyone understand what this means? Are there any people, if you understand what this means, please type in like a yes. Okay, cool. So there's a little bit of confusion. Let's re-explain this. Okay, so some people understand and some people don't. All right, let's redo this. Say that we have this sequence, and we know that there are certain cows that are bad. These are bad cows, these are bad cows, these are bad cows, and these are bad cows, right? Do we all agree that you can just ignore all the cows that are outside the border of we can ignore all the good cows that are outside the border of the bad cows? Like all we have to look at is this area, and we can ignore everything outside. Does that is there anyone who doesn't understand why this is true? Okay, awesome. So in fact, we can just ignore this. And we can always assume that we begin with a bad cow chunk and we end with a bad cow chunk, right? For our analysis. Make sense? If it doesn't make sense, let me know. All right. So what we're going for here is to draw a relationship between our greedy algorithm and the fancy algorithm. Our fancy algorithm is to do as much work as possible and then fix the problems along the way. And then our greedy algorithm is the whole point is to do as little work as we can along the way. And we want to formally prove their equivalence. So we need an expression, we need a formula. So for our number of how, like for our greedy algorithm, what determines our number of moves in terms of bad cow chunks and good cow chunks? What's the formula for the number of moves that we'll have to make with our greedy algorithm? Our greedy algorithm. Exactly. So the formula for the number of moves is equal to the number of bad chunks. Does that make sense? Because you have this chunk that you can flip at the same time, you have this chunk that you can flip at the same time, and then this chunk that you can flip at the same time. And every time you can flip a chunk. You don't have to flip more than a chunk, you don't have to flip less than a chunk. Does this make sense? Does it make sense? Go ahead and type in yes, or if not, just type in no and I can re-explain everything. I'll give it a moment to sink in. Sure, I can say it again. Our greedy algorithm goes to all the cows and it identifies which cows are bad, right? And once you determine which cows are bad, we can group them into chunks, contiguous chunks. This is a contiguous chunk, this is a contiguous chunk, and this is a contiguous chunk. And remember, the cool machine can flip everything in a chunk at the same time. So that saves moves, right? And so how many moves does your greedy algorithm have to take? It's just simply the number of bad chunks, because you go to every single bad chunk and then you flip everything in the bad chunk and then you get the correct answer. Does that make sense? So this is the exact number of moves that our greedy algorithm will take, expressed in a simple formula. Does that make sense, Jimmy? Okay, cool. All right, yeah, so let me know if there are any further questions. Now we want to figure out, well, how many moves is the cool fancy algorithm going to take, right? So how many moves is the cool fancy algorithm going to take? Does anyone want to present like a simple formula for it? So how can we describe the number of moves that it will take? Yes, exactly, from Kevin. It is 1 plus the number of good chunks. Great, so we have expressions for both of these. And how do we relate these together? How do we relate these together? So there's actually a very direct relationship between the number of bad chunks and the number of good chunks. Does anyone want to point out what this is? Ah, yes. Okay, so Jonathan has the right answer. If you look at this sequence, it'll become apparent that the good chunks and the number of bad chunks have a very specific relationship. And that is, if I know that I have 3 bad chunks in a sequence, I know for sure that they're separated, right? If these chunks of bad cows were not separated, then we only have 1 chunk of bad cows, right? And so if they were only separated by 1 chunk of good cows, then they would only be we would only have 2 chunks of bad cows, and etc. So in fact, there's also a third relationship that we can describe here, which is the number of good chunks is equal to 1 minus, oh, sorry, no. It's the number of bad chunks minus 1. Does it make sense why this is true? Or if it doesn't make sense, just type in a no in the chat and then I'll see if I can provide more intuition. So for Kevin, yes, your third formula is correct, but the other two are never true. I think the third one is always true. Does it make sense why this is true for people? So for Kevin, yes, it's true that like there are more possible situations, but we've established that if there are any extra things that are correct out here, we'll just ignore all of them. And so case 3 is the only case that we'll have to care about. Okay. So it seems like this might be a point of possible confusion. For people that don't understand, would you mind just letting me know in the chat so I know where everyone is? Oh, so does everyone understand? If you understand, please also let me know in the chat. This is a very important part, and so I want to make sure that people are following. Okay, great. So we have this relationship, and we can actually draw the equivalence now, because your cool fancy algorithm took 1 plus the number of good chunks, but we also said that the number of good chunks is the number of bad chunks minus 1. So what happens when you actually evaluate this? This is actually the same thing as the number of bad chunks. And the key here is to notice that the greedy algorithm accomplishes the same task in the same number of moves. And so, you know, there's a key thing to draw from here, which is our cool fancy algorithm did more work than it had to do. It said, okay, let me take any sequence of good and bad chunks and let me flip a bunch of things. Let me flip things that are not supposed to be flipped. Let me flip good chunks into bad chunks in an effort to try to save work by flipping bad chunks at the same time. What we showed is that any cool fancy algorithm that does more work than it has to do ends up doing the same amount of work as the greedy algorithm. And we prove this because there's an equation and they match. And that's the beautiful part of greedy algorithms. That's actually what makes them also very tricky, which is that there is no unified way of solving greedy algorithms. You can, for a lot of problems, the greedy algorithm will look correct, but it won't actually be correct. For example, in that plane flight planning, travel planning situation, or if you have coins of weird denominations. In fact, if they're not like the United States denominations, like pennies, quarters, nickels, dimes, etc., if you have like weird denominations that don't have this nice factorization structure, making change for those coins is also not a greedy problem. So the tricky part about greedy is not actually implementing the solution. It's to think very carefully about why the greedy solution is actually correct. And just to walk you guys all through it again, we originally had this idea. We were like, oh, there's this greedy algorithm. We can just ignore all the things that are already correct. These things are already correct. We'll never want to flip them. So let's just go through and flip all the ones that are incorrect, trying to chunk them together so we can flip things together to minimize work. That's the greedy algorithm. But then we had another thought. We were like, doesn't it actually save work if we flip multiple bad chunks together and then we somehow fix the things that we messed up in the middle? We considered it. And then we had this debate. Almost 50% of people thought that the greedy algorithm was incorrect and that it would have failure cases. We thought about failure cases. We thought about a lot of them, and none of them broke the greedy algorithm. So the more failure cases that we saw that did not actually break the greedy algorithm, we became suspicious. We were like, maybe this greedy algorithm is actually correct. And then we sat down and we actually thought about it, and we proved that any algorithm that does extra work is stupid. Like it's not worth it to do any of that extra work, because you end up doing the same number of flips as the greedy algorithm. So this step-by-step process of first identifying, using your intuition, a possible greedy algorithm. Second, trying to see if any obvious failure cases will break the greedy algorithm. And then third, actually sitting down and thinking about it more carefully and proving to yourself that the greedy algorithm is correct is this three-step process is sort of like the way that you want to solve these problems. There's a little bit of a more formal way that I can describe solutions to greedy problems. Like if you take an algorithms class in college, they'll say that there are two things that are required. The first is optimal substructures, and the second thing is local greedy decisions lead to global optima. These are basically just fancy words for things that we already discussed in today's lecture. So in some sense, this is basically like how you would be taught greedy algorithms at the college level. Like this is basically what they do. And the hard part is to be able to write this proof out for more complicated cases. But hopefully this proof was pretty intuitive. Sort of like we showed that you can actually write specific expressions that describe the number of moves that it'll take in certain situations, and we showed that they're the same thing. And once you get to college and you take this class, you'll see that the solution that we came up with, or this problem, also has these two properties that lead to the existence of a greedy solution. Cool. Does that make sense? Does anyone have any questions before we actually implement this in App Inventor? And if there are no questions, just go ahead and and react with a thumbs up in Zoom like I'm doing right now. So I can gauge how people are doing. Okay, great. Yeah. So let's go ahead and implement this. Let's go to MIT App Inventor. All right, so it'd be great if you could follow along with me. Programming is a pretty instructive process. And so yeah, just go to MIT App Inventor, hit create apps. I'll log in with my account. And I will create a new project. So I will go to start a new project. What is the project name? Well, this thing is called Problem 2, Mad Scientist. So USACO Mad Scientist. And I hope you all can see my screen. Just go ahead and type like an OK in the chat once you're done and you're at this screen where you have this stuff. Hold on, and I'll give people a moment to do that while I set things up. And in the meantime, I'll also pull up AirDroid Cast so I can cast my phone to the screen. And so you'll be able to see all the stuff that I'm doing as well. Okay, where's MIT App Inventor? Oh, there we go. Okay. All right, so hopefully you don't need too much more time. So okay, cool. So let's just build out our interface. We need an input text box to read in our input, and then we have a button here. I am going to leave this as an input. We need it to be multi-line. The height should be automatic, but let's width fill parent, this text. let's say this one should be solve. And, we'll make the width fill the parent. And we'll also put a label. And let's say that the solution will go here. Width fill parent. And for this label, we will, I always like to keep the names of my components consistent. That way I know exactly what I'm doing. And for labels, I use this LBL thing, just to indicate that it's a label. And let's call it the answer label. This one is a button, so I'll name it btn underscore button. This button is just like the solve button. And then this text box input. Right, so these are the three components that we need. Let me scan the QR code so that, we can test the app in real time. Okay, great. So I have this here. And cool, so I can hit solve, I can type in an input and it's multi-line, we can hit solve. So yeah, if you're up to this point, type in an okay in the chat. And if you're not, just like, let me know that you need more time. I'll give people a few moments to get this all in order. But yeah, don't worry if the greedy algorithm thing seems a little bit daunting to like have to, avoid all the trap cases that people might throw at you. It becomes easier over time as you see more greedy problems, and you'll be able to develop your intuition to be faster at proving that these things are optimal. But I hope it was a fun exercise to see how like we can blend algorithms with simple formulas to show very simple properties of algorithms to show that they're correct and stuff like that. So yeah, anyone need more time, or can I move forward? Okay, I think I'll just move forward. Onwards, exactly. Love the energy. Okay, so let's create some, let's think about it. So first we need a callback, right? Because when somebody presses our button, we'll need to do something. And let's read it into a variable. Let's initialize a local variable. This will be our input. And this will be a thing that we read from our text box. So our text box will have some text, so we'll read it in. And we need to parse it, right? And remember, we'll have to look at the USACO site to see what the input looks like. The input looks like a number in the first line, and then something in the second line, and something in the third line. So in fact, we probably want to initialize this. This is the raw input, but then we'll need three variables. So the first so maybe, we'll create another variable, and sometimes I forget how to make one. Okay, there we go. Local. This is going to be the split. Input split, because we want to split the input by the return character so that we can read in the inputs. Hopefully this is something that you've all done before. So I forget sometimes split. Okay, so split the text, and we don't even need this first variable, so maybe just delete this. So we'll have this input split, and we'll split this text at this character reverse n. Hopefully this works. I am not sure if they handle escapes correctly. But let's take a look. We have our input split, and one super nice tool that I like for debugging is to use a notifier. So let me drag in a notifier, and then the notifier can just print stuff for me. So when I do notifier.showAlert, maybe I'll just show the input and make sure that it's being split correctly. So let me go ahead and I think the input companion disconnected, so I'll have to fix this. All right, so I will go to connect, scan the QR code. Yeah, so Evan, yeah, I haven't worked with MIT Unbenefit in a while, and I just want to make sure that the \n actually parses as a new line. I think it will. I have hope. So if I type in n some like characters and characters. Okay, great. So you can see in the notify that it actually split it as a bunch of list items, and each list item was in fact the thing that was in one of the lines. So that's perfect. Then we'll need to form a few variables. Let's say that the first index should be n, right? So we need to initialize a new variable. And we will initialize this one to n. This should be our number. And we can go to list and we can index in list. Well, I actually don't remember how to get select list item. I think that's it. So our list is our input split. And the index is just going to be, is MIT App Center 1 index or 0 indexed? Can someone remind me? Okay, it's 1 index. Perfect. Thank you very much for the save. I think there's another thing that we might want to do. I think you should be able to parse numbers, right? Can we parse numbers from strings? Someone remind me if this is possible, or if it just automatically gets turned into a number. I guess we could just do this number plus 0. That might make it parse as a number. If anyone has any better ideas, let me know. Okay, you think it already goes to integer? Okay, perfect. Hopefully that'll be the case. And then let's create another few variables, right? Because we have n, and then we have a few strings. We have the A string and we also have the B string. So the A string is just going to be this thing at index 2 and then this one at index 3. Cool. So we have our inputs. Let's create a procedure. Yeah. I guess we could just create a procedure here. So let's create a procedure to do some stuff. We'll want to take in our inputs. We'll rename them N, A, and B. Whoops, this thing is still X3. And so we just need to count. So remember that the problem itself basically just asked us to count the number of flips that we would need. And the number of flips is actually just the number of chunks of bad cows. So does anyone have any proposals for a simple algorithm that could count the number of contiguous chunks of bad cows? Hint, it should only take one for loop over the entire list. Aha, yes. So Bowen has a very elegant answer. If it's a good cow, just add 1, because if it's a good cow and you had a bunch of bad cows that came before it, then you can just add 1. Now we'll have to be a little bit careful because, for example, if the first cow is good, then we don't want to do anything. Yeah, like we'll just have to be a little bit more careful. But yeah, basically the idea is very simple. And it's correct. So if we encounter like a bunch of bad cows and we're just going to collect all of them into the same one, we don't need to increment it. But then if it flips and it changes to a good cow pair, then we'll have to change it. Okay, so let's implement that. We'll just want a for loop. We want a for loop and we want it to go to n, right? And get n. We want to increment it. And so we want to figure out the 2 cases. We have a control that says if, and we'll want to select, oh, can we select the index of a string? How do we do that? I guess we could use segment, yeah. Oh, that's a little bit annoying. Okay, so we'll want to logic, sure. Yeah, is there an easy way to change a string into a list in MIT App Inventor? I don't think there is, but this isn't a big deal. Yeah, I don't think this is a big deal. Cool. So we'll just change this to I. The text will say this is the A text. And then we'll start it at index I and we'll get it at length 1. And we'll want to check whether it's equal to the B text length 1. So this is the case where they're the same, and then there's also a case where they're different. So we also want to initialize probably a variable. Initialize this variable, and we'll want to say this is your answer. We'll initialize it to 0. So we initialize it to 0, and we say, okay, well, currently, we want to, first of all, like the relevant information would be, do we currently have a running count of cows that are bad? And if we do, we'll want to like add that count to the answer. So let's initialize 2 variables. This variable describes whether we have a running count of bad cows. So in bad cow chunk. And we'll initially just initialize this to false because you're not. And if they're not equal, then we'll want to say, well, if they're not equal, then we currently are in a bad cow chunk, right? Then we are in a bad cow chunk. And if we're not, then we'll want to say another thing. So if they're both good cows and also we are in a bad cow chunk, then we want to add 1 to our answer, right? Because previously we saw a huge chunk of bad cows, and then we currently just saw a good cow. Then we'll need to break this chunk, and we'll want to add 1 to the answer. So we want another if statement. So let's duplicate this and get rid of all these old things. We want to say if how do we get bad cow chunk? If you're actually in a bad cow chunk, if we're in a bad cow chunk, then we'll want to add 1. So we go to answer, and we set answer to we'll add 1 to it. Add 1 to answer. So if we're in the bad cow chunk and we see cows that are good, then we'll just add 1 to the answer because we don't want it. Otherwise, what should we do? Well, we don't really need to do anything. We can get rid of this. But then every time we see we're in like a good cow chunk, we should also set the bad cow chunk to false. There's one more thing that we need to take care of, which is this takes care of the case where you end on a good chunk. What if you end on a bad chunk? You actually never add that to the correct answer, right? So we need to do a final check after the for loop. If we ended on a bad cow chunk, we never got to add 1 to the answer like we should have. So if at the end we're still in a bad cow chunk, we should add 1 to the answer. That's something that we should do. And then finally, we should just return the answer. And I'm not sure if there's like an easy way to do this. There's like an easy way to plug this into a return value. Ah, yes. This might be it. Right? So we can create a procedure that takes in this thing and it would do this, and the result would be, what would the result be? The result would be get answer, right? Oh no. You can't do that. That's really sad. Okay, well, it's fine. We'll just hack this together for now. We'll call this the solve procedure. And at the very end, all we'll do is we'll just take the label answer and we'll set the text to the answer. And here we can just call the solve procedure with N A and B. Okay. So no promises that this code actually works. Let's check it. This is where the checking comes in. So let's go to AirDroid, and I need to rescan the QR code, but then let's go ahead and try to verify that the solution is actually correct. So one thing that we can do is just directly copy these things. We can copy the sample input into MIT App Miner and actually just set this as the default value. So we can go to here and we can type in this text, and it turns out that it'll just show up here. So if we hit solve, it'll say 2. Okay, so the answer is correct for this case. Remember that we said there's like a little bit of an edge case where if you end on a bad cow chunk, we'll never add that if we don't do that last check. So let's add a bad cow chunk here where it should have been G, but it was actually H. It gives us 3. Perfect. We can now stress test our solution. If you go to the USACO website and you go back to the problem list, you can actually scroll down and download a bunch of test data. So this test data will have super large cases that can help you test your solution more carefully. So the first one was obviously, let's open this in VS Code. The first one was obviously really simple, right? This one was our example case. But what about the second one? This one has 200 cows. So this one, if we get this one right, it would be pretty promising. So what we can do is we can go in into text box input. I'll type this in the chat for anyone who's trying to use it. But we can put this into the text, and you can see here, now we have to hit solve, and then so our answer is 39. And yeah, looks like it actually gives us 39, which is the correct answer. So we can go ahead and try this for even larger cases. This one was 406 bytes. This one is 800 bytes. So this one should be around 400 cows. And indeed, it's exactly 400. So then we can copy 400 and also type this in if you're wanting to check your own solution. You can put it into this text box, then it'll automatically update on your phone. You hit solve. This one says 76. What's the correct answer? 76. Let's see if we can do a crazy one. This one is 2 kilobytes. 2 kilobytes. This one is 1,000 cows. Let's see if MIT App Miner actually is able to run this. So we have 1,000 cows here. We're actually unable to scroll. So we have to go to MIT App Miner, and you can go to the main. I think if you go to the main viewer, the main screen, you can change the property scrollable. And so if you hit this one, it'll make it scrollable. So now you see we have 1,000 cows here, and we can hit solve, and the answer is 183. Let's see if this is right. So we can go to 10.out, and it's actually 183. So yeah, we've checked it against basically all of the test cases in the USACO database, and or we checked it against some of them, but we checked it against the largest one. So I think we're reasonably confident that this is the correct answer, and so this should be the solution. And hopefully that's a useful demonstration of how you should test your code. But yeah, let's go through this one last time, just so we make sure everyone's on the same page. Here's our code. Basically, all this code does is it counts the number of contiguous chunks of bad cows. And we proved that this was actually the right way to solve the problem, because we showed that this greedy algorithm of just looking at the bad cows and flipping all the bad cows over is just as equivalent to any solution that does any more work, that flips other things and then tries to fix the problems that come in the middle. So we reduce this problem to just counting the number of bad cow chunks. And so all this does is it iterates through the list, and it keeps a running count of what's going on. So if A is not equal to B at this current index, then the situation is you have an incorrect cow. So then we're like, okay, we're in a bad cow chunk. But what's the condition for adding one to the answer? Well, you only want to add one to the answer for any time you encounter a phase change. So you can have a whole run of bad cows, and then once you see the next good cow, it means you can't flip them together. So then you have to just register the entire bad cow chunk that you were currently in as another chunk that you have to process. So you add one to the answer. And then of course, because this current chunk is a good cow chunk, we can set bad cow chunk to false. And then finally, at the very end, there was this edge case where you didn't, if you ended on a good chunk, you would be fine. But then if you ended on a bad chunk, you actually never got the opportunity to add one to the answer like you should have. So then we add one more to the answer. And that's it. We can set the label answer to get answer. If you have any further questions, let me know. In the meantime, I will publish this to the gallery. Actually, I'll freeze my screen here. And in the meantime, I'll publish this to the gallery. So that it's available for your reference. So the description, image file. Oh, I have to choose a picture. Just choose this one. Okay. Did it publish? I'm confused. Okay, yeah, it did publish. Okay, I can send the permalink to you guys. Permalink is here. And yeah, cool. So hopefully, yeah, so that's pretty much all I had for you guys today. Just to recap, we talked about a new problem-solving paradigm called greedy solutions. Greedy algorithms. Greedy algorithms are super powerful because they're super simple. They're kind of like no-brainer solutions. They're almost things that seem too good to be true. But what we showed we can do is we can think about it carefully, and we can oftentimes prove that greedy algorithms are optimal just by thinking carefully about it and drawing equivalences between greedy solutions and more complicated ones that we might be considering. So yeah, and so it turns out that greedy solutions, even though you can think about the fact that there are so many different ways that you can flip cows such that you arrive at the right answer, it's remarkable that the correct answer is just so simple. It's you just flip all the cows that are wrong. And then it turns out that the implementation is just this simple. We did it in like 10 minutes. So yeah, hopefully that gives you a taste for the kinds of greedy algorithms that you might encounter in competition, and hope this was useful.
Okay, great. Thank you, Kevin. Well, guys, you're gonna check out the master document for your homework, right? So we're not gonna spend more time explaining the homework assignments, but it's available in the master document. But for now, so we have a couple of minutes. If you have any questions, you can ask. You can talk with Kevin. Maybe you want to ask some questions. Maybe you want to get some advices or any other things you can talk. Yeah. So. Yeah, you can unmute yourself, speak it up, or otherwise you can type in the chat. Okay, I got a question for Kevin. What is the first programming language did you learn?
I first started programming on MIT App Inventor. It's a I think it was back in like 7th or 8th grade. Yeah, it was a lot of fun. Like MIT App Inventor is great because it doesn't take you a long time to get your to get your feet on the ground running, because you can immediately start building very cool applications, like things that you can actually interact with, things that you can actually put on your phone and show your friends. Not the case with Python. With Python or Java or like JavaScript, it'd probably take you years, multiple years, at least 1 year, to be able to build apps that are as powerful as the ones you can build in MIT App Inventor. So yeah, I mean, I think it's a great way to get started. And then in the future, there's there's really no barrier to progressing into general purpose programming languages. Yeah, it's just overall a great learning platform.
Okay, so after MIT App Inventor, what was your story? I mean, in your high school, what was your journey studying, computer science or programming in your high school?
Yeah, I don't know. I mean, throughout high school, I just I first, after I left middle school, after I spent about like 1 or 2 years learning MIT App Inventor, I started learning Java, I started learning Python, I started learning C++. And then I became interested in AI. So I just kind of drew me in that direction. But the skills that I picked up from MIT App Inventor have stuck with me since. This like whole building applications thing. It's always been a key part of the stuff that I build, which is I always want to make a demo. I always want to make something that I can show people. So yeah.
Okay, what are you doing now? And what's your future plan?
What am I doing now? I'm currently spending a lot of time doing research. I work in AI. I work on large language models, like GPT, things that you might have been using to write your homework essays these days. So I work on those things. For the future, I'm not totally sure. I think I might spend some time just building random projects, or doing more research in this area. I think, there's a lot of exciting stuff to do, and it's all very fun. So can't make a wrong decision.
Okay, you get a question over there.
What
From
programming
Kevin.
language is my favorite? I don't have a very strong opinion about this. I can tell you my least favorite programming language. It's JavaScript. It's just very frustrating to work with. But I mean, I write most of my code in Python these days, because that's what some of the most popular machine learning frameworks are using. So that's sort of what I use. But yeah, I'm not a huge programming languages person. Like there are some programming languages junkies who will have very strong opinions on the art and science of designing programming languages. And there's like a deep field of theory there. And it's very fascinating, but I don't know anything about it. So yeah, I'll just go with the normie answer. Python's pretty nice. Yeah, so Scratch is an interesting platform. I think the reason I like App Inventor a lot is because they let you put apps on phones almost like kind of natively, which is really incredible to me. I don't know if Scratch has improved their offering over the years, but my impression was that it was mostly something that you could mess with in your um, browser. Like you can make interactive games and stuff in your browser, but you couldn't actually put it on your phone and show your friends and build apps that people could use. And that's kind of like the main draw of App Inventor to me. Super nice. Opinion on esoteric programming languages. Yeah, I think sometimes people just get bored and they try new things and they make these like programming languages that are super strange. Some of them have very vulgar words. I mean, like vulgar names that I'm not even allowed to say probably. But usually the case is that every single programming language has its own strengths, has its own benefits. Like otherwise people wouldn't use it. So if you've heard of Go, Go is like a relatively new language. I wouldn't call it esoteric, but it's less popular. And its specialty is supporting concurrent processes. So if you're doing a lot of multi-threading, then Go is the way to go. There's also Rust, which is super high performance. There's also a nice mechanisms for memory management. Memory management is just how you store things, and like it's one of the key banes of existences of systems programming. So yeah, every single language sort of has its own use cases. Some are faster, some are slower, some are nicer to read and write, some are harder to read and write, all for their own uses. Does crypto suck? Uh, yeah, it's very much up to opinion. I mean, if you've heard of like the whole FTX thing, that thing is pretty interesting. I
No, I
hope
was
none of
just
you have been
kidding.
affected by it.
I was just
I
kidding.
hope none of you have money on FTX because it doesn't look like we're getting that back. But yeah, crypto is interesting. I think I'm a little bit more optimistic about the cyberpunk kind of DeFi decentralization people rather than the people who are in it just to make money. There's a lot of interesting cryptography going on now in crypto. I mean, believe it or not, for a long time there was no cryptography in crypto. It was just all money making schemes and distributed systems. But people are now doing things like zero knowledge proofs. They can basically transform. The goal is for them to change the way that we do governance, to like be able to prove certain things about yourself without revealing who you are. If you're interested in politics, this is a huge problem because, for example, if you have a Republican senator, they will always vote with the Republicans, no matter whether they actually think that the Republicans are pushing the right thing, because if they don't, then they'll not get reelected and stuff. So some people have been proposing zero knowledge systems that can, prove like, hey, a Republican voted for this legislation, or a Democrat voted for this legislation without actually revealing who their name is. And that could give people a little bit more freedom to vote against party lines if it's better for the world or something like that. So yeah, I think crypto is cool in some ways, but also it suffers from the same problems as traditional finance. It suffers from the same like faults of human, I don't know, greed. Yeah. Opinion on C#. I haven't used C# a lot. I think the last time I used it was in Unity. Like if you've ever done any 3D modeling, Unity is super fun. And like I did a little bit of programming in Unity, just like very, very little. I didn't really learn C#, so I thought it was fine. It was kind of confusing because I didn't really know it. I'm getting an echo. Yeah, that's exciting. I remember echoes are pretty fun. You just got to make sure to like mute them so they don't accidentally listen to you and send all your data to Jeff. But yeah, echoes are fun. Oh, echo in this meeting. Sorry, yeah. You should probably mute for Dr. Mang. Okay, yeah, sorry. Yeah, hopefully that should fix it. Will I be back for other classes? Maybe. Yeah, so I'm a college student right now and it's break for me, but it gets a little bit busy during the semester, but I will do my best in case. I mean, if the class was good, if it was bad and you guys hate me, just let me know. But also if it was good, I'll try to be back at some point. But what about pictures of monkeys and wearing clothes? Yeah, I agree. I'm guessing this is a reference to NFTs. I think NFTs are cute. It's a little strange that like people are willing to pay so much for these very abstract things. I don't know, people would pay a lot of money for ownership. It's pretty funny, but I don't know, to each their own. Economies are all about demand and supply. So if people demand pictures of monkeys wearing weird clothes, like, so be it. Yeah, $8 internet check marks. Elon is kind of just like, I don't know. One way to look at it is he's screwing everything up. Another way to look at it is he's kind of breathing life into Twitter. I hope like a lot of these changes don't stay. I don't know if you guys heard, but there was like this funny story where there was like a somebody who made a fake impersonation account of like a super large pharmaceutical company, and they fake announced that this pharmaceutical company was making insulin free, and then it like absolutely tanked their stock and wiped out a lot of value for their investors and stakeholders. So it was really funny, but also it's a little bit dangerous if you think about it. Like, good, pharma is greedy, and they probably kind of deserved it. Insulin should be nowhere near as expensive as it actually is. It's terrible, but it's fascinating how much power Twitter has over the entire world. Yeah, the Nestle thing was hilarious. There were like governments. There were, Trump was, I think, at some point impersonated. All of it was funny. But it's also kind of dangerous. So I hope they like get rid of this blue checkmark thing, or they like turn it green or turn it purple or something else, so that we can actually tell who's verified and who's not. But yeah. 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 The Rahul and Daniel thing was also hilarious. Yeah, it's just a wild time to be on the internet right now. I honestly, I was Rahul actually like, was he actually an employee? I kind of doubt that, but maybe he actually was. But like they were rehired. Oh, no. Yeah, I saw this. Yeah, Elon posted a tweet and he was like, "Oh, welcome back, Rahul." Yeah, Elon is a man of the people, kind of, depending on how you look at it. Yeah, I'm not gonna say the last names. I am currently being recorded. I don't know what VeggieTales Twitter is, and I honestly don't want to know. If it got banned, I'm sure it was banned for a good reason. Opinion on game design. That I have some friends who really love making games, and I think sometimes as people who play games but don't actually design them, we kind of underestimate how complicated and how much thought goes into designing games. So yeah, I think it's a very deep subject. It's very complicated. It's by no means trivial, and it's cool. Like if you're ever interested in it, I'm sure there are probably good tutorials on the internet about designing games, right? Because just like off the top of my head, you need to make sure that there's a coherent story that people can understand and intuit the dynamics of the game quickly so that they can actually make meaningful progress. You need to make it somehow emotionally engaging. You need to make it, you need to make money from it too. That's often really hard, and people often default to like freemium models where you just get people to pay for gems and stuff. And it's just sometimes people are annoyed by that. Yeah, so it's complicated, but it's really, really fun. So yeah, I encourage you to explore that if it's something you're interested in. And it can also be very meaningful. I mean, because gamification of educational content is becoming increasingly popular. You can see it with like Duolingo, you can see it with Kahoot. Those are all gamifications of stuff like that. So yeah, I mean, MIT App Vendor can probably be used to make some games, although I know that some of my friends also used Scratch when they were kids. Yeah, the Duolingo thing. Yeah, mobile Minecraft ripoffs. I don't know if you guys ever played Survival Craft. That was fun. For Jonathan, why are your variables not being set?
事，
Um,
再睇，
I'm not
再
totally sure. If
問
you want to
啲
like
問題，
share
佢就
your
去講呢啲
screen, you
嘢
could
啊！
probably fix
你
that
唔識
or
得係咪？
yeah, I don't know. MIT App Vendor can be kind of tricky with how they initialize variables.
因為而家唔係嗰個時候，上完課啦，而家就係問 extra 問題，因為要等到10點啦。
That's Cantonese, right? Okay, yeah, never mind. I think it's being muted.
Yeah, Survival Craft was great. But what do you mean genre of its own? It was basically Minecraft. We can't lie about that. It was better? How is it better? $7 less? Wasn't Survival Craft like $4? Minecraft was $7, right? It was $3 less. Yeah, I don't know, man. Survival Craft was like the stuff that the kids who couldn't afford Minecraft played, like myself. All right, anyways. It was super fun hanging out. I think that's all the time that we have. Go forth and enjoy the rest of your break, and good luck with the rest of the class. Super fun having you guys.
Okay, thank you, Kevin, and everyone. Good night. And okay, goodbye. Yeah, goodbye. Yeah, have a great holiday.